So we're going to be talking about chapter 10.1, which is all about correlation. In correlation, we are focused on scatter plots and the relationship between bivariate data. So we're going to be describing what is that correlation relationship between two quantitative variables and find a way to measure the strength of that linear association. When we talk about bivariate data, this is focused on paired data that we want to see, is there some type of relationship or association between? Typically, this is where we have collected data from some type of study or experiment, and we're looking at an explanatory variable and a response variable. So an explanatory variable is the independent variable. It's when the variable that is being manipulated or observed to see, does it have some type of effect on the response variable. So here I put, for example, if you're studying the effect of study time on test scores, the study time would be considered our explanatory variable. This is typically your x variable. The response variable is your y variable. That is your dependent variable. So all of those are meaning the same thing, but this is what we are measuring as an outcome of the study. So it is what is measured, observed to see how it responded to that change of the explanatory variable. In that same example, the test score is the outcome and the response of the study time. So the test score is our response variable. A little bit of notation. We have x and y variables. Y is the response variable. And we can also notate a y with a subscript I. This could be y1, y2, y3, y4, all this so on. So that is the individual response for that person or object that we're observing. Y hat is the predicted value for that response for that particular individual. Whereas x is our explanatory variable, so xi, x1, x2, x3 is the individual x value that was observed. When we're looking at bivariate data, a scatter plot is the most useful relationship or most useful graph to see that relationship. We would put our explanatory variable on the x-axis and the response variable on the y-axis. And then we look to see what is that relationship going on between the two variables. So here we have a data set of different jackpot winning amounts and the number of tickets sold based off of that ticket amount, or sorry, that jackpot amount. So we can see when the jackpot was at 334, the number of tickets sold was 54. If we create the scatter plot for this, we can do that in Excel or we can do that in R. For Excel, we would highlight our data. Let me zoom in. So we highlight the data, do insert, scatter plot. And there's our relationship. We can see that as the jackpot winning amount increases, they are selling more tickets, probably because more people want to win, so more people are buying tickets. If you need to add chart elements, you can add axis titles, a chart title, and we can even add a trend line, which we're going to be doing in regression for 10.2. Part of this, you might see formatting your trend line. You can add the equation and r squared value onto that graph. So in this scatter plot, this is the regression model that we will find eventually in 10.2. The correlation is what's measuring that direction and strength of this linear relationship. Correlation R is what we are using. It is sometimes referred to as Pearson's correlation coefficient, and it's a value that ranges from -1 to +1. If we had a graph that had a perfectly straight positive line, it would be a correlation R equals 1. The direction is indicated by that sign, whether it's positive or negative. So if you have a negative R, it's a negative relationship. You'll see a scatter plot with a decreasing trend. The magnitude indicates the strength. So the closer we are to -1 or +1 would indicate a stronger relationship. If we're stuck here in the middle, we are closer to having no relationship. So if R is 0, there is no relationship, no linear relationship between the two variables. We do want to be careful and make sure that we understand that this correlation coefficient only measures the strength of the linear relationship between the two variables. It does not account for if there may be some nonlinear relationship between the two variables. So here are a few hypothetical examples to give you a visual representation of what that correlation coefficient might be. We can see this perfectly straight positive scatter plot gives me R equals 1, compared to perfectly negative is at -1. Typically, we would not see something perfectly straight like that. So we might have a scatter plot that looks something closer to this negative trend here. I would still call this a strong negative linear relationship. And then if we went to 0.88, we see a strong positive linear relationship. This in the middle, there's really no general upward trend or downward trend. We can see it's all just kind of scattered about and not really following any trend at all. So it has a correlation coefficient close to 0. So this is at 0.3. Notice in these examples how R is going to change. So we have a very strong positive relationship in this scatter plot, except there is an outlier in this one. This outlier is affecting the relationship of R. So that correlation that I would expect to be very strong is now lower because of this outlier. We also see in this one a very clear nonlinear scatter plot. R is still measuring the linear relationship between these two variables, and there's certainly not a linear relationship, but we have to have an R value. That correlation value is -0.15, which is very close to 0. So it would say there's no correlation because there's no linear correlation. We'll look at how do we assess some kind of nonlinear relationship later. The correlation R has another variable R squared that we also talk about often in relation to it because they are connected. R squared is called the coefficient of determination. This is what's measuring the percent of variation in the response variable that is accounted for by this linear relationship between x and y. It is the square of R. So if we had R squared as 0.873, as a percent, that's 87.3%. So we would say 87.3% of the variation in whatever y variable we're talking about is explained by this linear relationship between x and y. The higher that percentage is, the better your linear model is explaining the relationship between that x and y variable. All right. When we're finding R and R squared, you can use Excel or R to do this. There's actually a few different ways, so I've modeled just a few here. In Excel in 152, we did this, and we did the equals CORREL, Correl, and then you highlighted your x and y variable data. You had to manually calculate R squared by squaring that R correlation coefficient that you found, or we saw it on the scatter plot. We can also do this in RStudio using the core function, and you would select your x variable and your y variable. R squared is going to be a lot easier to find once we do linear regression in R and in Excel. But for now, you can still square that correlation value that you get. Here you can see in this scatter plot, I went ahead and displayed the R squared value. But I can also do Corel and highlight my X and Y variable data. The order did not matter necessarily, but it does give me a correlation coefficient R of 0.947. Let me move that over and say R is equal to this. We can also do this with the data analysis. So if I were to highlight my data, we can go to our data analysis and go to regression. Here we have, I've already went in and put in my Y variable. So here's my Y variable, my X variable range, the jackpot, and then I do have the labels already included in that selection, so I want to click on this labels option. You will need to select where do you want your output. So when I click over here for output range that was originally blank, I just click on an empty cell, so I can put it here in D2. You could also put this in a new workbook if you really wanted to. And then you decide what things do you additionally want to calculate. These are stuff that we will talk about in 10.2. So if I click on that summary output, it's doing a lot of statistics analysis that we don't necessarily need yet. Here we can see this multiple R. That is the exact same value as this R that we just found. So this multiple R is your correlation coefficient. We also see the R squared value. There's some other things that we will talk about eventually, but for now, those are the two values that we have in 10.1. As we get to 10.2, we'll talk about these coefficients that create the equation. Now, if I did this in RStudio, I've already input my data set, so we could look at a plot. This data set is named jackpot, and I want to specify we're looking at the jackpot and the tickets. So here we can see we have our jackpot on our x-axis and tickets on our y-axis. If I just wanted to find the correlation between these, it's asking you to do x and y. Our x variable was the jackpot, and our y variable was tickets. That correlation 0.947, we found the same value in in Excel. Now, if we wanted R squared, the way to do this right now is just to square that correlation coefficient. So I just took that same correlation and squared, and it's given me 0.897. As you get into 10.2, you'll learn some other ways to find that correlation coefficient if needed. Now, optionally, we can also talk about a hypothesis test for correlation. This is a formal hypothesis that can be conducted for our correlation between the two variables. This uses the Greek letter rho. This is what it looks like. It looks like a little P. And that's representing the linear correlation coefficient for the population. Remember, for our hypothesis tests, the parameter is typically used by some Greek letter like mu, was for our mean. Here we have rho for the correlation coefficient. Now, what we assume is that there's no correlation between the two variables. So if there's no correlation, then that correlation coefficient would be 0. We are also testing the alternative hypothesis that there is a correlation. So if there is a correlation, then it's just not 0. You could test to see that there's a positive correlation or a negative correlation if you want, but for right now, we're just maybe looking to see, is there some type of linear relationship between these two variables? We would use the test statistic formula here. It is a t-test statistic, so we're going to do a t-test. This r is the correlation coefficient we found from our sample data. And we use n minus 2 degrees of freedom. If we have a sample size of 9, which is what's happening in that jackpot data, the sample size is 9 paired data values, so there'd be 7 degrees of freedom. And we can calculate this with our Excel, doing t.dist.2t. I'll do that here. So we first want to figure out what is that test statistic. And we just found r, so it was r divided by the square root of, and then we have a fraction inside that square root. So we're going to want parentheses 1 minus r squared divided by n minus 2. So n minus 2 here, there were 9 paired data values. So n minus 2 would be 7. And we get a test statistic of 7.83-ish. Our p-value, we could do t.dist.2t since this is a two-tailed test. We did a not equal to in our alternative hypothesis. So our test statistic I found here was 7.83-ish. Degrees of freedom is 7. That gives me an extremely small p-value. That p-value is 0.0001. So since the p-value is small, we would reject our null hypothesis. So I reject that rho equals 0, that the correlation is 0, which means I have reason to believe that there is some type of linear correlation between the two variables. This is a little bit of a prelude for what you're about to see. So the p-value 0.0001 is the same as this p-value here for the jackpot variable. We'll talk about what that means in 10.2. So for now, we're focused on, can we first create a scatter plot and also describe the linear relationship between these two variables. We do not want to rely on r solely, the correlation coefficient r. That's a description of the strength of the two variables. However, just because something has a strong r correlation coefficient does not necessarily mean that the whole thing is best modeled by a linear model. So we'll see that again come up later in 10.2 and a little bit more in 10.5.